Hi, welcome back to this machine learning fundamentals tutorial. In this video, we'll be talking about evaluation. Understanding how to assess a machine learning model is crucial for ensuring its effectiveness and reliability. So let's explore various techniques used to evaluate both classification and regression models and learn how to apply these in real-world scenarios. So, importance of model evaluation. Evaluating a model is essential to ensure that it performs well, not just on the training data, but also on unseen data. The process helps us gauge the model's accuracy, prevent overfitting, and determine its readiness for real world applications. So, remember our example about data splitting, where you don't give it all your data when you're trying to teach the model, train the model. There are different train test splits. So you can say, okay, I'll give it 70% of my data to learn, to train with 70%, and I'll leave out 30% to test how it is doing. So that is the train test split. You can also have a 90-10 split. So you train with 90% of your data, and then you leave out 10% for testing. So there are different splits 70-30, 80-20, 90-10, and so on. But there's also something like the validation set. The validation set is basically testing while you're training, while the test set is when you finish training, you then test it. So that is what it means. So you can have a train of 70%, validation 15%, test 15%. So now let's look at types of evaluation matrix. So different types of problems require different metrics. So we have classification metrics like accuracy, precision, recall, and so on. Regression metrics like mean absolute error, mean squared error, and so on. Let's look at classification metrics. So here we have accuracy, precision, and recall, F1 score, ROC, AUC. The accuracy is basically overall how often is the model correct. So it measures how the model makes the right prediction, how often that happens. So it's like checking how many answers you got right on a test out of all the questions you answered. That is accuracy. Then we have precision and recall. So precision tells you how accurate your model's positive predictions are. So imagine you made a machine to pick out apples from a mix of fruits. So precision measures how many apples picked by the machine were actually apples. Then we have recall. So recall measures how good your model is at catching all the possible correct cases. So let's continue with the apple picker machine. So if there were 100 apples in total and the machine picked 90 of them, then the recall is how many of those 100 apples the machine managed to pick. So that is it. Then we have F1 score. So it combines precision and recall into one number. It helps balance the trade-off between precision and recall. So if you want a single score to see how well your apple picker is doing, considering both how many are really apples and how many apples it picks, the F1 score is your answer. Then we have the ROC-AUC curve. So ROC, receiver operating characteristic curve, and AUC, area under the curve, measures how well your model can distinguish between two things. So it's like sick versus healthy people. AUC tells you the chance that the model can correctly identify a randomly chosen positive instance, like a sick person, as being more likely than a randomly chosen negative one, a healthy person. So a higher AUC value means the model is better at telling the difference between the classes. So when I also said positive and negative, it doesn't mean like the actual instance. Sometimes you might choose a class to be your positive class and another class to be your negative class. So you can say someone having a disease is the positive class, while someone not having the disease, the healthy person, is the negative class. So now let's look at regression metrics. We have mean absolute error, MAE, MSE, and R squared. The MAE measures the average mistake made by the model in its predictions. For example, if you predicted the weight of several puppies and compare your predictions to their actual weights, MAE tells you how far off you are on average. It doesn't matter if you predicted too high or too low, it looks at how big the mistake was. While with mean squared error, it also measures the average mistake made by the model, but it gives more weight to larger errors. So this means that if you make a big mistake in your prediction, MSE will punish you more than MAE would. So it's like being in a dart game where missing the target by a wide margin costs you more points than being slightly off. So that's how MSE is. Then we have R squared. So the portion of the variance in the dependent variable that is predictable from the independent variable. So it measures how well your predictions match the actual data. So it's a way of seeing how much of the change in your data can be explained by a model. For example, if you are predicting students' test scores based on their hours of study, the R square tells you how much of the differences in their scores can be explained by the hours they studied. So that is the regression matrix. Let's look at cross-validation. So it's a robust method for assessing how well a model generalizes to an independent dataset. It involves dividing the dataset into multiple parts, using different sections for training and testing in multiple rounds. So imagine you have a recipe for a cake, but you want to make sure it tastes good before serving it to everyone. So to test the recipe, you bake a few small cakes and taste each one to check if the recipe works well. So cross-validation is like this taste testing process, but for machine learning models. So you split your data, remember? So like a collection of cake recipes or data about cake, you divide this data set into several parts or folds. Then you train and test this. So you train your model on some of these parts and test it on the remaining parts. So this means you use different parts of your data for training and testing each time. And you repeat this process multiple times, each time using a different part of the data for testing and the rest for training. So this helps in getting a better idea of how well your model performs on different data. Then you average the results. So after testing on all the different parts, you average the results to get an overall picture of your model's performance. And it's good for better evaluation, and it also reduces overfitting. So overfitting, so it checks if your model is too specifically tuned to the training data and ensures it performs well on unseen data. So now let's look at the confusion matrix. So it's a table used to describe the performance of a classification model on a set of data for which the true values are known. It lays out the predictions of the model in comparison to the actual classifications across two dimensions, the predicted values and the true values. So the confusion matrix for a binary classification problem has two rows and two columns, but it can be expanded for multi-class classification problems. So here we have, if it's a binary classification problems, we have the following. So we have true positives. So these are cases in which the model correctly predicts the positive class. For example, if the model correctly predicts that a patient has a disease, these predictions are true positive. So if having a disease is your positive class, and the model says this is a disease and it actually is a disease, that means that is true positive. It correctly predicted that that patient had a disease. Then we have true negatives. So these are cases in which the model correctly predicts the negative class. For instance, if the model correctly predicts that a patient does not have a disease, these predictions are true negatives. So for example, remember healthy is the negative class in our example. So if the system says does not have a disease, that means this person is healthy and it's actually true that you confirmed and you checked that that person was healthy, that's a true negative. Then we have false positive. And these are the cases in which the model incorrectly predicts the positive class. So this type of error is often called a type 1 error. For example, if the model incorrectly predicts that a healthy patient has a disease, these are false positives. So remember, it says the person has a disease. That's from the positive class, and it is false. You checked, and that was a healthy person. Then we have false negatives. So these are cases in which the model incorrectly predicts the negative class. So this type of error is known as type 2 error. For example, if the model fails to detect a disease in a patient who actually has the disease, these are false negatives. So, for example, it says, okay, they don't have the disease, and you checked, and that person actually has the disease. So that means you said something was in the negative class, but it is false. So that's the confusion matrix. So remember our different metrics? So remember you had accuracy, precision, recall, and F1 score. And there are different ways that you can calculate this. And that's how you get the confusion matrix. So if you want to calculate accuracy, that is true positive and plus true negative divided by true positive plus false negative plus true negative plus false positive. So basically true positive plus true negative divided by everything you have in your data set. If you want to calculate precisions, that's true positive divided by true positive plus false positive. If you want to calculate recall, that is true positive divided by true positive plus false negatives. If you want to calculate the F1 score, it is 2 times precision times recall divided by precision plus recall. So to conclude, understanding model evaluation is crucial for developing reliable, effective machine learning models. So thank you for watching. In the next video, you'll see our practical aspects of different machine learning algorithms. Thank you for watching.